I want to do a little demo. I've got a magnet here. Okay. This magnet only works really appropriately when it's cool. Sometimes magnetic strength is related to how cool the magnet is. So what I'm going to do is I have some liquid nitrogen over here. I'm just going to cool it down a little bit. Cool it down a little bit. Now notice the nitrogen doesn't stick. Why is that? To the magnet. Because we just did an MO diagram and we found out it's diamagnetic. So it should not stick to the magnet, right? Okay. Now, what I've been working on here for a while is making some liquid oxygen. Liquid oxygen is kind of a baby blue. It's a little hard to see the pretty color, liquid oxygen. But I'm going to pour it in the magnet. And it sticks. That's what my son says too. Got a little more. You can see that it's sticking to the sides, but it's not sticking in the middle. That's because oxygen, we just did the MO diagram, is paramagnetic. So it better be magnetic. And it is. And I think that's the last bit I have. Pretty cool, huh? Otherwise, not at all. By the way, is liquid oxygen flammable? Have I asked this already? Is oxygen flammable? I don't know if I asked that. What do you think? Is oxygen flammable? Sort of. It's not. If I had a pure oxygen gas and I put a flame in it, would it burn? It wouldn't, because there's nothing to burn with. There's nothing combustible. You need something flammable in order for it to burn. And so just oxygen itself wouldn't be flammable, but because everything around us, you, me, the chairs, etc., the building is flammable, then it's kind of considered a flammable. So that's why I don't make very much of it. Okay. Because the oxygen liquid is just has so much oxygen gas in it, all compressed together. Okay. So we're going to do more examples of MO theory next time. But now you've got the gist of it. You should be able to draw an MO diagram for any homonuclear compound up to neon. Okay, you can practice with your friends at home, I guess. And you can say, hey, give me a molecule. And they're like, oh, fluorine 2, -1. And then you can say, watch this, I'll draw the MO diagram. On page of the textbook, on page 420, it gives you all the answers to the neutrals. On page 420 of the textbook is a diagram like this. Even tells you the bond order and the magnetism. So this is a great way to practice just using this figure from the textbook. Okay. So you can also check that out when you practice, and we'll practice more at the next class. Okay. But otherwise, we have finished section 5, and we're going on to section 2. Remember, we're going backwards in textbook time space. Which would be, let's see what page. In the reader, it's just the next page. As you flip over, that would be page 105. In the textbook, that's page 400 and following. The section 6 and following the textbook, we're not going to cover explicitly. You can just read for fun. They're also in the reader as well. You can read those for fun. But we are going to cover sections 2 and 3, which I'm going to do. I'll do section 2 first. And, yeah. Valence bond theory is something we're not really going to use, but it introduces the next topic. If I take carbon, for example, its electron configuration is this. It's made up of s and p orbitals. So this is methane, for example. Oh, what are the bond angles on methane? 109.5 because it's tetrahedral. I didn't draw a tetrahedral, but that would be the bond angle. But the weird thing about the orbitals, if you draw out the orbitals, kind of like this, there's the orbitals. If you look at the orbitals and you put the angles of the orbitals together, what angles would the p orbitals make? They make 90-degree bond angles. Well, the problem is, from what we know of carbon, it would make 90-degree angles, but it doesn't. It makes 109.5 in this example. So the angles of the orbitals do not match with the angles produced by VSEPR. The angles produced by the orbitals themselves is called valence bond theory, which in this case they produce 90-degree angles because the p orbitals are orthogonal to each other. But that's not what we get from VSEPR or experimentally. We get more 109.5. So we wonder, how do these make these angles that look so different? And that's the end of section 2. Section 3 and 4 come from. Section 3 and 4 are hybridization. Okay, so valence bond theory, that's all we're going to say about it. Kind of just for us, intros the next topic, which is hybridization. They're all bonding theories. So now, so far we have Lewis bonding theory, MO, we have valence bond, and we have hybridization. Hybridization and MO are actually related. That's why I wanted to do MO first. And also, I don't want to end on MO, you'll freak out. Hybridization, just like your Prius, is a mixture of two things. In that case, a combustion engine and electrical battery power. It's a hybrid of those. Hybridization, chemically, is a similar sort of thing. Take the s orbital and one of the p orbitals. These both have wave functions. Remember that vaguely from chapter 7? You say this is the 2px, for example. Mathematically, I could add these wave functions. So just on a sketch basis, remember these are both functions, described mathematically. On a sketch basis, it would kind of look like this. And let me make the S a different color. Blue. Okay. In this case, the unshades would add. The same shades would be additive, in that case the unshades, to make a big fat lobe on the top. And the shade with the unshade would have destructive interference and make a little baby lobe on the bottom. So if I mathematically add an s and a p orbital, I get this kind of offset looking orbital that's fat on one side and a little tiny part on the other. This would be a hybridization between an s and a p orbital. Okay, so let's go through the 3 standard examples. The first one is with CH4, which is tetrahedral. I drew it up above. This is tetrahedral. Has a 109.5 degree bond angle. Okay. We say, to explain that angle, what we say is the following. If you draw the energy orbital line diagram for only the valence electrons, the 2s and the 2p, 2s2, 2p2. There's the electron configuration. We say this hybridizes. And this is how we explain this shape. We say it hybridizes, and those 4 orbitals, 1 2s and 3 of the 2p's, mix together, just like your cookie and you're mixing ingredients. They mix together to make 4 new orbitals. We can name those orbitals anything. Josephine, Brian, Peggy, whatever. But we choose to name them sp3. Okay? These are 4 sp3 hybridized orbitals. And those 4 electrons go 1 in each orbital. Let me show you this schematically in an artistic rendering. I'm going to zoom in a little bit. When we take these four orbitals, we mathematically add their functions. When we do that, we get these four new orbitals right there, which you can see there's a larger part and a smaller part. When we put them together, amazingly, scientifically, magically, those form a tetrahedral shape with 109.5 degree bonding. So our guess of hybridization as a model fits what we see experimentally. So we would say that the CH4, the methane molecule, forms sp3 hybrid orbitals to get that shape that matches with Vesper. Okay? All right, let's see what magically happens with the rest of the class. Okay, now let's take a different example. And where carbon is kind of our, the standard example that everybody uses, and it's one that we talk about a lot, especially in the OCHEP. Okay, so carbon, this is a different carbon molecule now having a double bond. What would the bond angle be? You get 120 because it's trigonal planar. Okay? So now this, again, I'm redrawing what I had up above, the orbital energy line diagram. 2s2, 2p2. We can't explain it with the previous hybrids because the previous hybridization gives a 109.5 degree bonding. So we explain it with this type of hybrid, a different type, which we say the following happens. In this case, instead of mixing all four orbitals together, we're mixing one of the s orbitals and two of the 2p orbitals together. And we're leaving one of the 2p's unhybridized. So one of those 2p's I'm not going to touch. I'm going to leave it all by itself. But the other three I'm going to mix together to make three new orbitals. Again, we can call this whatever we want. We can call it, Isaac. We could call it Yuki, whatever we wanted to. We call them sp2 hybridized orbitals. Okay? And those three electrons go here. We call it sp2 because it's one part s, the 2s orbital, and two parts p, the two 2p orbitals. Yeah.
What is that with sp2 and the one before it?
The one before is called sp3. This one right here you're talking about? Yeah, because it's a totally different hybrid. In this case, you're fixing one part s, the 2s, and three parts p, three 2p orbitals. So it's just that kind of notation. Again, we could have called it anything, but it definitely is different. It's fully different because now, let's show you the diagram. Artistic rendering here. We're starting off, and these are all in your text if you want to see them. One of the s's and two of the p's, and we're mathematically adding them. Again, it's just mathematically adding them. And then, when you put those new orbitals, again, they look similar. They're not the same, but they look similar with a larger end and a smaller side. Two different sides. But when you put them together, scientifically, mathematically, magically, they form 120 degree bond angles in the trigonal planar shape, which is the shape that we're trying to match. So what it turns out is, we use this model of sp2 hybrids to explain what we see experimentally happening with this molecule. Okay? So this is just a model down here, hybridization model, to explain what we're seeing actually happen. Okay? There's all kinds of different hybrids. You've seen two now. All kinds of ways that things can actually hybridize. Is there a question? Okay, go ahead. I don't see you.
Right here.
Okay.
Okay, so we have you don't have for this one. The cleans, these two planar molecules. But then I know that there's what's happening about here.
What's the difference?
For the two trigonal planar space clean. We have each part. How do you know which one is part?
How do we know, wait, what's perpendicular? It looks planar to me.
I know it's all planar, but then when my PA drew it out, he got it to that the hydrogens were perpendicular.
To the other two hydrogens?
Yeah.
It's a different molecule. That's an aldene, which has two double bonds. Okay, one last hybridization to explain this carbon molecule. This carbon molecule, we need a different hybridization because this is experimentally different. What's the shape of this one? It's called linear, right? Two groups. What's the bond angle? 180. 360 divided by 2. So now, we need to explain how do you get a linear molecule, or how do you get that something that's 180 degrees? Well, we explained that through a third type of hybridization. Again, the starting point is the same. We have a carbon molecule that's unhybridized, 2s2, 2p2. And we say, okay, how can this hybridize in order to get these kinds of bond angles in this kind of shape? Well, what we say is one of the s's and one of the p's hybridize, and the two of the 2p stay the same. So those first two 2p's, I'm going to keep the same. And then I'm going to hybridize an s with a 2p. So if I get a different color, hopefully you can see this. These two are going to hybridize here, and these two are going to stay the same. So two are going to hybridize, two are going to stay the same. The two that hybridize, because it's one part s and one part p, we call it sp hybrid orbital. What does this look like on a schematic sense? In this case, when you mathematically take an s and a p orbital and you add them together, you're going to get these two orbitals, mathematically again. And then, when you put those two orbitals together, again, magically, scientifically, however you explain it, you get this. Okay? Again, it's just adding these to orbitals. You get the linear shape and the 180-degree bond angle. So now, we're saying that this type of model, this hybridization model of SP, matches what we see experimentally. So what we say is, we think this carbon in this molecule is being sp hybridized. Okay? So those are three types of hybridizations. Let me write those out for you on a different page. Your question. Oh, because I forgot to draw them. Is that your question? I don't see you either. I don't hear you more. You're pulled out. Okay, yeah. Is that what I forgot? Okay. All right. So, what hybrids are there? Well, you've seen the SP. I'm going to leave a little space above this. You see the SP2 and you see the SP3. The SP3 happens when there's 4 groups. The SP2 occurs when there's 3 groups. And the SP happens when there's 2 groups. Those are the ones that are easy to draw out, so I drew those out for you. When there's 5 groups, do you see how I've used up all 3 p orbitals? So what do you think I have tacked on here now when I need an additional group? Yeah, a D. And when there's 6 groups, we call that an octahedral, it's sp3, and what do you think? D2. If there were 7 groups, which actually occurs, it'd be sp3, D3, all the way up to 5, and then you finish the d orbitals. And this is not actually a hybrid, but when there's 1 group, it'll just be a s orbital. Okay? So notice when you fill up the s's, then you add the p's. Once the p's fill up, you start adding these. And those are the names of the hybrid orbitals that form. We're not going to draw these other ones, 5 and 6. They're just a little too complicated for our class. Again, in physical chemistry or inorganic chemistry, you'll have the joy and opportunity to draw stuff like that. Okay? We're not going to do that here. What's that? That's right. When I say groups, same terminology as before. He's asking, what do I mean? I mean the groups around the center atom, just like we count groups in Vespers. So if I rewind just a moment. So a way of doing this problem, we're going to do the problem in reverse. When we do a problem on a vinyl, we'll say, oh, 2 groups on this carbon, it's sp hybridized. We'll look at this carbon, 1, 2, 3 groups, trigonal planar, sp2 hybridized. And when we look at the first one that I drew, which I don't know where it is, here, CH4, 1, 2, 3, 4 groups, that's sp3 hybridized, it's a tetrahedron. Okay? So we're going to actually determine hybridization through counting groups. Will be the easiest way for us to do it. Okay, one more thing now. I just want to show you this so you can see where things come from. You don't have to be able to draw this. But a carbon, a CH4, if I draw the CH4, will have 4 sp3 hybrid orbitals, and it'll bond to a hydrogen. The hydrogen is just an s orbital. And that's what methane will look like. Each sp3 hybridized orbital will bring 1 electron, and each hydrogen will bring the second electron. And that's how the bond forms. There's 2 electrons, so there's the bond. These are sp3 hybridized orbitals, and this is an s orbital, specifically a 1s. So in this bond, the CH bond, you should know that it's between the sp3 hybridized orbital of a carbon to that 1s orbital of a hydrogen. That's what the bond would be. And if you go back a little bit in the notes to here, here's the sp3 hybridized orbitals. Notice there's 1 electron in each orbital, and that's why I put 1 electron in each sp3 hybridized orbital. Okay, second thing we can say about this, what kind of bond? All 4 of these are what kind of bond? Sigma or pi? They're all sigma bonds, because the bond is occurring between the 2 center points of the atoms, occurring between the center points. So these form, they're all sigma bonds. So this molecule has a total of 4 sigma bonds, in this molecule, for example. All right, let's draw another one. We had that, this one. Okay. And that one, that's the one I drew second. This has what kind of hybridization? SP what? 2. Previous one was SP3, this is SP2. Okay? So how does this work? Again, I'm going to draw a picture like this. You won't have to draw something like this on the final, but I'm drawing it so you understand where I get this information. All right. Okay. So each carbon, I'm going to have to draw this kind of big, has 3 sp2 hybridized orbitals. In the trigonal planar fashion, 120-degree bond orbitals. So now let me draw the carbon. That's carbon on the left. Let's draw the carbon on the right. Okay, like that. Each one of those has 1 electron in it. 1, 1, 1, and then for the other one, 1, 1, 1. Okay? They're surrounded by hydrogen. So let's draw the hydrogens now. Hydrogens are s orbitals, one s orbital specifically. They overlap, their orbitals overlap to make a bond. Each hydrogen brings one electron. One. Okay? See, two electrons form a bond. Now, if you look back at the sp2 hybridized in your notes, what have I not drawn here? I've not drawn the 2p. Let me show you. I'll come back to this in just a moment. It's this one in the middle. I drew 3 sp2s for each carbon, but I have not drawn the 2p yet. Does that make sense? Let's draw it now. Why not? Okay, the 2p orbital, I'll draw that in blue, would be perpendicular to this plane. There's one of the 2p's on that carbon, draw the other one on this carbon. Okay, this is a 2p, this is a 2p. Each one of these carries one electron if you look at the picture. Now I have to draw it so it's somewhat readable, but actually these orbitals are so big that both p orbitals would be overlapping with each other. Okay, but I just drew them real skinny. Yeah. Why is there 2 of the 2p's? Because there's 2 carbons, and each carbon has one 2p. Okay, these would actually overlap, and I'll draw 3 lines just to show that they're overlapping, they're touching. These are not a triple bond, it just means they're touching. Okay. All right, now notice, every carbon-hydrogen bond is what kind of bond? A sigma bond. Does that make sense? The bond happens between the center points. This carbon-carbon bond has 2 bonds. What's this one called up here? That's called a sigma because it's between the center. What's this other bond called? It's called a pi. That means a double bond, you see where I'm going to head is, a double bond equals a sigma and a pi bond together. The sigma and pi bond, so a double bond is not 2 bonds that are the same, they're actually 2 different bonds. One is a sigma bond, the second one's a pi bond. They're different. Sigma bonds are actually noticeably stronger than pi bonds. Sigma bonds don't break easily because you can free rotate and it doesn't break a sigma bond. But if you rotate the pi bond, which is happening like this, once you rotate it, it breaks it because you break the plane. So pi bonds are a little weaker. So a double bond is not twice as strong as a single bond. It's stronger, but not twice as strong. Okay? So know that every double bond has a sigma and a pi. So in this molecule, how many total pi bonds do I have? Yeah, I have a total of 1 pi. How many total sigma bonds do I have? You should count 5, right? 1, 2, 3, 4, 5. Okay? You should be able to count totals. Okay. So, let's just look here. This is back to the sp hybridized orbital over here. For the sp hybridized orbital, those 2p orbitals, what do you think they're going to do? One of them is going to form the second bond, another one's going to form the third bond. So in a triple bond, whenever you see a triple bond, that means there's a sigma and 2 pi bonds. So in this molecule, right here, what's the total bonds? First of all, how many pi's are there? You should say 2. And how many sigmas are there? You should say 3. 1 in the middle, and 1 here, and 1 here. Okay? All right, let's pause there. We're going to do a lot of examples next time and talk about fire.